Okay, so this is the final lecture for the Introduction to Analytic Number Theory series. So yesterday, I guess we were discussing equidistribution, and in that context, I raised the question of the equidistribution of angles of Gauss sums. So we equidistribution. I mean, sometimes some of these questions can be very complicated. So what did we do? We did the following. So P is a prime. And we considered Z mod PZ. And we defined the Gauss sum for a character to be I mean, I might have used psi of AX. Okay, so I call this psi of A of X. And we showed that this was equal to chi of A tau sub 1 of chi. Maybe there's a bar there or something. Okay. So that we should that. And then we also showed that the absolute value of tau 1 of chi is square root of P if chi is a non-trivial character. And interesting result in its own right. And then the question arises as to how the angles, so this, we can write these, we can write the tau 1 of chi as square root P e to the I theta P of chi, where theta P of chi is, an angle between 0 and 2 pi. And we can ask, as P varies, as P tends to infinity, are the numbers if you want, by the way, we could put 2 pi I if you want. I mean, it doesn't really matter. So that my thing is between 0 and 1 now. Are the numbers theta P of chi in this interval 0, 1 equidistributed? Sometimes, by the way, you also use the word uniformly distributed, equidistributed. So applying Weyl's criterion, we need to study the following sums. We need to study, these sums, either 2 pi I m theta P of chi, where I am running over all the characters chi not equal to chi 0. How many characters are there? They're multiplicative characters. So the number of characters is p minus 1, and then I'm not taking the trivial character, so it's p minus 2. Okay? So I have to now take the average and show and check whether this goes to 0 as p goes to infinity. Right? This is the way, this is what Herman Weyl would tell us to do if we want to check for equidistribution. So the either 2 pi I m theta p chi is the mth power, i.e. this guy is the mth power So we have to check this. We have to study this. So let's do that. Let's try to study this. And let's bring out the p to the m over 2 outside. And then the mth power of the Gauss sum. So remember that this is just chi of x psi of, keeping in mind what psi is, of course, okay, psi of x mod p. We raise it to the mth power. Right. Okay. So when I expand this, so it's 1 over p. So when I expand it, I get x1 xm chi of x1 chi of xm psi of x1. So this is an additive character. Psi of x1 times psi of x2 is psi of x1 plus x2. It's an additive character. And this is a multiplicative character. So this is really product of x1 to xm. Goes there, right? And so now what we'd like to do is we'd like to interchange summation. I mean, you have no choice when you see two sums, unless you want to be stuck. You have no choice, right? 1 over p to the m over 2. Of course, everything converges absolutely, so there's no problem here. Now we recall our orthogonality relations for Dirichlet characters. So recall that summation chi of A as a sum over all the characters is equal to phi of Q, well, in this case it's phi of P, right? It's just P is prime, right? So it's a so if A is congruent to 1 mod P and 0 otherwise, right? This is how we have our characters. So the only problem here is we have we're not summing over all the characters, we're summing over all but one. Okay? So we have, I can modify this when it's the trivial character, chi of any trivial character is always 1 anyway. So chi of A, chi not trivial, well that's P minus 1, it's P minus 2 if A is congruent to 1 mod P, okay? And it's minus 1 otherwise. Okay. So this means that this sum here equals 1 over P to the M over 2, 1 over P minus 1, P minus 2 rather, times psi of x1 xm with the proviso that the product x1 xm is congruent to 1 mod P. And then I pick up, in that case, a P minus 1. Yeah. P minus 2. Yeah, sorry, P minus 2. I'm here. And then when otherwise, I pick up a minus 1. Product is not congruent to 1 mod P. Fair enough? So there's P minus 2 here. Yeah, did I put a, there's a minus sign here. Okay, good, okay. P minus 2 here can be written as P minus 1 minus 1, right? And I can combine one of these with the minus 1, congruent to 1 mod P and not congruent to 1 mod P for the full thing. But then it's an additive character, and it doesn't really matter what this sum is. So a little bit of tinkering to do here. So we can combine the minus 1 with the other one, so we end up getting here x1 xn minus 1 over P to the M over 2, P minus 2, summation Are you okay with that? There's no condition on the x1 to xn because the plus 1 and not congruent to 1 and not congruent to 1 have been now combined. There's no need to put anything further, okay? Now this, what is this? Well, this can be written as psi of some A, for A, times n sub A, where n sub A is the number of solutions of x1 to xm, so the sum is equal to A, right? Mod P, of course, it's mod P. Well, I can pick x1 in P ways. x2 in p ways, etc. And then finally, xm is solved after I pick all the earlier ones. So the number of solutions is, once I've picked m minus one of them, the x sub m is unique. Therefore, the number of solutions for this thing is equal to p to the power m minus 1. I mean, you'll see in a while this is actually irrelevant, but anyway, let's do it carefully. So the number of solutions does not depend on A. This number comes outside. And then now I have to figure out what summation psi of A is. But psi is an additive character. I'm going over the full, which is a non-trivial additive character, and I'm going over the full group. By orthogonality for the additive group, I get that it's 0. Okay, so this whole thing just gets wiped out. Hope that's clear. A little bit of thought shows that that gets wiped out. Okay? Well, this sum, you want to write it as what? Yeah, you could have done that too. That's true. Yeah, that's a good point. Yeah, he's right. He says that instead of doing it this way, you could have also written this as product summation psi of x I, like so, and xi is the subscript here is the variable, so I is going from 1 to m or something, and so the inside sum is 0. So you can see it that way too. Yeah, it's true. Good point. So in any case, this is 0, and now we're left with this thing. Okay, so as I said, it starts off with a very innocent question. I give you Gauss sum. I ask you how these angles are distributed. You try to do the wild criterion, and all of a sudden you end up getting into a problem of this kind. And this is not a joke to solve. This is what's called a Hyper-Kloosterman sum. Let's see what the trivial estimate is. I can pick x1 any way I please, x2 any way I please, up to, firstly, all these xi's have to be, a product has to be congruent to 1 mod p, therefore they have to be relatively prime to p. So the choices of where x1 is p minus 1. For x2, it's p minus 1, so on and so forth, until I come to m minus 1. And having picked all the m minus 1, x sub m is pinned down by this congruence. So therefore, the number of choices for the x1 to xm is p minus 1 to the power m minus 1. Exactly. P minus 1 to the power m minus 1 choices. For each such choice, this is at most 1, right? Therefore, the trivial estimate for that particular sum is p minus 1 to the power m. Everyone okay with this? Okay? Now, let's see if I can use the trivial estimate and try and plug it in here and see what kind of thing I get. Just notice that this is practically 1. P minus 1 over p minus 2 is practically 1. I have a p to the m over 2 here, and so this is no good. Absolutely no good. In order to win, I've got to get the numerator almost like a square root. Okay, and so that's actually a result. That's a theorem of Deligne. Okay, so this is the theorem of Deligne. And he proved it as a consequence of this Weil conjectures. So this is why he got the Fields Medal. So this is stuff that comes out of algebraic geometry. So intertwining of algebraic geometry and number theory again. There are these famous conjectures called Weil conjectures, which again, that'll be a nice mini course one could give on Weil conjectures for a week or so and get you rolling. So I won't discuss that here, but the fact is that the trivial estimate is p minus 1 to the power m, and so Deligne proved that it's bounded by p to the power m minus 1 over 2. O of that, where O is some fixed. Okay, so that is enough now, because you can see that should be enough because we have 1 over root p finally, which goes to 0. So in order to answer the question of equidistribution of the angles of Gauss sums, you need wave conjectures. It's a theorem that was proved in 1974 by this guy. So as the non-trivial stuff all of a sudden gets injected into the picture. Now that's very fascinating and very interesting, but this is a good example of how a very innocent looking question can lead you into deeper waters. Okay. On the topic of Gauss sums, let me introduce another function called Jacoby Son. So if I take chi and I better not use, let's take chi and let's take chi 1 and chi 2, multiplicative characters, mod p. Then the Jacoby sum is equal to this function. And the Jacoby sum is quite useful in number theory, and it can be, just as I told you yesterday, that the Gauss sum can be thought of as the analog, the finite field analog of the gamma function. Similarly, the Jacoby sum can be thought of as the finite field analog of the beta function. If you remember the beta function in I forgot exactly what it's 1 minus x to the t dx. Something like this. Maybe there's an s minus 1, I'm not sure. Is there a minus 1 there? Okay, minus 1 there and minus 1 there too? Oh. Okay, well anyway, it's something looking like this. So here again, the function x goes to x to the s is a multiplicative character on the reals. So these are two multiplicative characters, and I've kind of intertwined the additive structure somehow in this fashion. Well, these sums are very interesting. Now, if you remember your basic calculus, as I said, don't take my word for this. There might be some fudging that I have to do here. But it essentially boils down to gamma of s, gamma of t, gamma of s over s plus t, right? I mean, you have this interesting identity. So it shouldn't come as a surprise if you take that proof mutatis mutandis, well, not quite, and use it here. Something like this is, so I'll leave this as an exercise. So in other words, the Jacoby sum can be reverted back to Gauss sums, and you have this nice, neat little exercise. So if you don't know how to do this, I suggest you try it. It's very easy. And if you still can't figure it out, I believe in my book on analytic number theory, I do discuss the beta function in the book. and you can just look at the proof of this fact and then mimic that in the finite field case. It works just perfectly fine. So actually, it's easier in the finite field case. Okay. So anyway, you have something like this. So it's an interesting phenomenon here. And I just thought that I might alert you to the fact that since these, we know the absolute value of these numbers, this is root p, if provided these are non-trivial. So if I've got chi1, chi1, chi2, not the trivial character, then the Jacoby sum is a complex number, absolute value, root p. And one can try to understand, again, the distribution of these angles if you want, and you can try and play with that, so I'll leave it for you to play with. But I just want to point out something interesting that you can do with this thing. So let's remember that if P is a prime congruent to 1 mod 4, we have the multiplicative group has order P minus 1. And 4 divides P minus 1. And by the way, this is a cyclic group. Okay, this is a cyclic group. And the character group of an abelian group is isomorphic to the abelian group started with. This is something called Pointryagin duality or whatever you want. Okay, so the character group of this is also isomorphic to Z mod PZ star. So it's also a cyclic group. And 4 divides P minus 1. Therefore, you know, in a cyclic group of order n, you take a divisor d of n, there's always an element of order d. Right? Because if you take your generator and raise that to n over d, that element has order d. Okay. So similarly, here, Z mod PZ star has a character of order 4. Because 4 divides P minus 1. Let chi be that order. Now let chi be that character, rather. That character. Be such a character. It has order 4, right? So chi to the power 4 is the trivial character. Okay. So chi to the power 4 of x is always 1. So that means this guy's got to be a 4th root of unity. So chi of x is either plus or minus 1 or plus or minus I, right? So it's either, these are the only values it can take. Oh, hold on for a second. Yeah? Oh, thanks, okay. Okay. It's my bag I have to take to Bhubaneswar, so better not forget that. Okay, so this character takes on only these values. And I can now go and look at, for such a character chi, we can look at the Jacoby sum. So let's give, so take that character and now consider j chi chi. Now consider with that character. So j chi chi is chi of a times chi of 1 minus a. So it's going to be a bunch of plus 1s or plus or minus 1s and plus or minus i's. Okay? Collect the plus or minus 1s together. They add up to some integer a. Okay? Collect the plus or minus i's together. They'll add up to some integer b times I. So my number looks like that. Right? Now the absolute value of j chi is, yeah, it's p. So this, as a complex number, it's p. So a squared plus, so this times its conjugate, a squared plus b squared is p. In other words, I've managed to show that if you give me a prime congruent to 1 mod 4, I can write it as sum of two squares, and here they are. You can get it through the Jacoby sum. What is the a and what is the b? Well, that's what they are. How many times the integers group together to give the a, the plus or minus i's to group together to give the b, and those are the two numbers that I use in order to write p as sum of two squares. Okay, this is one of the, this proof is due to Eisenstein, so it's not my proof. I can't take credit for it, but it's a very slick proof. Poor guy died at the age of 24, I think. It's one of these tragedies. Norwegian genius, of course, and died very, very young. Okay, so that's takes care of that. Let me say a few more words about general techniques. So I hope I've given you some flavor of how equidistribution works. Given an equidistribution question, sometimes the mechanics, the framework of zeta functions, L functions works, sometimes it doesn't. I gave you examples where it does and where it doesn't. So this is certainly a case, the Kloosterman sum business was a case in point where you just don't need to put zeta functions and stuff like that there. Sometimes it doesn't work, so you have to kind of look at each situation. But generally speaking, the overarching kind of philosophy in number theory is the philosophy of equidistribution. You're trying to figure out a whole bunch of numbers, how are they behaving? Are they stuck in one place? Are they moving around? Are they kind of equally distributed? What kind of properties can we say? So from that perspective, you have mechanisms, of course, to study general problems that are given to you. Sometimes these things work through methods of zeta functions and so on and so forth. So let me give you this other example that I promised earlier, and that is this business of counting abelian groups. So let G of n be the number of abelian groups of order n, counted, of course, up to isomorphism, counted okay, and so you want to can we study summation G of n less than x? I mean, this is generally, I give you an arithmetic function. This is what number theorists do, right? I give you a function. I'd like to know how the summatory function behaves. This is what we've been doing from the very beginning. So I give you this function now. Can you tell me something about this? Well, and the answer is, surprisingly, you can. So on the face of it, this problem doesn't look like it has anything to do with Dirichlet series or anything like that. It looks like an algebra question, but it turns out that it has a lot to do with Dirichlet series. Okay, so this is, so here's a joke for you. What is purple and commutes? What's purple and commutes? An abelian grape. Okay. Now, after the little joke, so the first question is, can we write down a formula for g of n? Okay. Now, you may recall there's something called the fundamental theorem of abelian groups. Fundamental theorem. Abelian groups. Any finite abelian group is isomorphic to a direct product of cyclic groups. Right? Fundamental theorem. Cyclic groups are the building blocks of all abelian groups. Okay? Every abelian group is a direct product of cyclic groups. And the point is that if when are two abelian groups isomorphic? Well, if their cyclic components are exactly the same. It's a unique factorization theorem for abelian groups. So if you gave me a natural number n, let me write it as a multiplicative notation like this: p alpha sub p. So I'm writing my natural number n as a product of prime powers uniquely, okay? And this theorem is telling me a group of order n is built up out of cyclic groups. And each cyclic group has its Sylow components, right? I mean, so the p primary parts, the part that comes from p is, so that means how many I have to look for the cyclic group of order p1 to the alpha 1, maybe I'll use alpha 1, beta 1, beta t. So this will factor, the group of order n will factor as a product of cyclic groups. For each prime p, the p primary component will also factor as a product of cyclic groups, and they'll all have to be of this shape, some powers of p. But then the p primary component has order p to the alpha p, therefore the order of this guy has to match this guy, therefore beta 1 to beta t has to be alpha p. Right. Okay, I'm using some bad notation here. I just realized that, but anyway, I'll deal with. I'll come up with another symbol at some point. So, in other words, I take each exponent that appears in the unique factorization, and I figure out how many ways I can partition it. Okay, so this leads us to study what's called a partition function, a function that was first studied by Hardy and Ramanujan. It's surprising that nobody studied it until, I mean, the asymptotics of it until they studied it, but that's what it is. It's a partition function. So let me define partition function. P of alpha, number of ways of writing alpha as beta 1 plus beta 2 plus beta t. T is varying also. How many ways can I decompose alpha? Now, we should put some sort of restriction because, as you know, any shuffle of this thing is still isomorphic to the same guy, up to order, right? So we'll put some sort of restriction on these. We'll just say they're just increasing. So we want to count these partitions with this kind of proviso. So as I said, the partition function was studied first. The asymptotic behavior was studied by Hardy and Ramanujan. In fact, Ramanujan had discovered the circle method in India before he actually went to England, and then discussed it further with Hardy when he was there, and then that's how the collaboration started. It was a very important collaboration. Unfortunately, Ramanujan died a little too early, so that the method couldn't be developed very well, and that was developed by Hardy and Littlewood after Ramanujan's death. Anyway, so you have this P of alpha. So here's the recipe then. If n is equal to P1 to the alpha 1, Pk to the alpha k is the unique factorization of n, into prime powers, then the number of abelian groups is the partition function, the product of these partition functions. In other words, it's a multiplicative function. So that you wouldn't have never, unless you used the fundamental theorem of abelian groups, you wouldn't have known that. So this is a multiplicative function. And so the method of Dirichlet series is kind of conveniently associated to this thing. So we can write this Dirichlet series as the product of, over the primes, it only depends on the exponent, right? One for each power, because it's a multiplicative function. And so the question now is, what is this Euler factor? What is this Euler factor? In other words, what is well, we'll just say P of 0 is 1 or something. So what is this power series? Because this is just a power series with x equal to 1 over P to the s. So what is this? Well, this question was answered by Euler way back when. Okay, so we'll look at that. How many is a generating function for the partition function? So if I were to look at this product, 1 plus x squared x squared, I'm going to write as x squared. Yeah. right? So in a partition, I'm decomposing, let's say, alpha into bits. So I can use a bunch of times 1s, a bunch of times 2s, a bunch of times 3s. So if I use, that's why I'm trying to write it like this. So all the 1s are being collected here. All the 2s will be collected here. All the 3s, so if I use it 2 times, this is the one that calc keeps track of that. So I keep doing this, right? 3 plus 3, so on and so forth. So you can see what I'm doing, and if I multiply this whole power series mess out, the coefficient of x to the n is exactly partition of n. So this thing is exactly equal to the way I wrote it, x to the alpha. Or j, or whatever. Is that okay to everybody? Yeah? So the first factor keeps track of how many times I'm using 1. The second factor, how many times I'm using 2, and so on and so forth. When I multiply this whole mess out, I collect terms, and I calculate how often x to the n shows up, and it tallies everything. This is something that you can just think about it at home if you don't see it off the top of your head. Okay, so now these are very easy. What is this? This is just a geometric series. Yeah, exactly. So it's 1 minus x inverse. The next one is 1 minus x squared inverse. 1 minus x cubed inverse. Dot, 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 right? So I figured out that power series. And so now I can answer this question here. This series, well, I have to plug in x equals p to the minus s. Right? Looks awfully familiar, right? Yeah, exactly. It's the product of zeta functions. So it's zeta of s, zeta of 2s, zeta of 3s, dot, dot, dot. So it is actually product zeta of ks. K going from 1 to infinity. You would have never guessed that. The Dirichlet series, counting the number of abelian groups of order n, is actually the product of Riemann zeta functions. You wouldn't have known that had you not had the structure theorem of abelian groups, had you not had some knowledge of the generating function of the partition function, and and then realize that this is a multiplicative function, so you can write it like this, and you would never guess that. I mean, in retrospect, of course, it's obvious, but you wouldn't have guessed it at the beginning. It's kind of very fascinating. Now, this interesting object tells me it is ripe for an application of the Tauberian theorem. So, I've already continued this silly thing. It's just a bit of calculation that you have to. So let me write this as zeta of s times the product from k equals 2 to infinity zeta of ks. I'll leave it to you to check that this is an analytic function for real part s bigger than a half, actually. Okay, so there's no problem, because the only problem is zeta 2s, and it's already analytic for real part s bigger than a half, and everything else is really, it's even 1/3, and more, it's getting smaller and smaller. Actually, it's getting closer and closer to 1. So this, an infinite product converges the tail. In the case of a series, the tails have to go to 0. In the case of an infinite product, the tail has to go to 1, right? So, and I'll leave it to you to check that this converges neatly. So here we are. This guy's got a pole at s equals 1. This is analytic, and I know exactly what the residue is. It's the product of the Riemann zeta functions at k equals 2 to infinity. So without any work, well, the Tauberian theorem, I can now apply the Tauberian theorem. Implies that summation n less than x, g of n, is asymptotic to c times x, where c is the product of the Riemann zeta functions from 2 to infinity. The average number of abelian groups of order n is the product of the zeta functions. It's the average number. Okay, so this is a nice application. Now, supposing I was interested in studying some sort of version of equidistribution. You see, another interesting thing is here, of course, the value of g of n is not in some fixed range. So we can't talk about how is it distributed and all that stuff. You know, it's actually a natural number after all. And this is telling the average value is c. But sometimes when you're given a sequence of numbers, one of the ways of studying kind of equidistribution style properties are looking at the moments of the function. So we may want to study summation n less than x, g of n to the power k. You may want to study moments like that. Okay? So now that I know what g of n looks like, here it is, I can write down if g of n is a multiplicative function, so it's any kth power of it. And so you can now write down, but now this time it's going to be p1 squared. Let's say I'm looking at the second moment. You can do this, so on and so forth. And it's not going to be this anymore. However, here's the little trick. I'm leaving it as an exercise. The little trick is the number of ways of writing 1. How many ways can you write 1 as sum of the things? Just one, right? One way. So p of 1 is actually 1. So this is really 1. Okay, 2, how many ways can I decompose 2? Well, I can decompose it as 2 alone, or 1 plus 1, right? So p of 2 is 2. But p of 2 is 2, all right, but this is already p to the 2s, and that converges for real part s bigger than a half already. So somehow you can factor this thing as 1 plus 1 over p to the s times something else which converges for real part s bigger than a half. Okay, so that you can factor this guy out. And this guy is very close to 1 minus 1 over p to the s inverse, because it starts off with 1 plus 1 over p to the s. So again, you have a zeta function that you can factor out, but this time the other fudge factor is not so simple like the product of the zeta functions. It'll be a little bit more complicated. However, it converges for real part s bigger than a half. Okay, so you could apply the Tauberian theorem one more time, and you can get that this is asymptotic to, so let's call this C1, C2x. Okay. Tauberian theorem tells you you can analytically continue with a simple pole at s equals 1. That's all it's got. Everything else is okay. So now you can do this for higher powers, k. The nice thing about higher powers is 1 to the power k is always 1. These might be getting higher and higher, but then these guys converge for real part s bigger than a half. So a little bit of analysis of the Euler factors allows you to deduce that for all these higher moments of this function, you can easily deduce by simple application. Of course, this requires a little work. And this is what I'm just mentioning as a problem for research. You can work this out and maybe write a little note and publish it or something. It might not be a bad idea as x goes to infinity. Because I don't think anybody really worked these moments out or what these constants are. Might be worth doing if you're looking for a summer research project. So that's that. So maybe instead of starting new things, perhaps I can try to tell you a little bit about current research and then stop. Of course, there are lots and lots of stuff to say, but maybe. So this business of moments is an interesting phenomenon in its own right. So let me say about something about Ramanujan's tau function. So Ramanujan kind of almost a century ago stumbled on a very important function, and this function has received considerable attention now. So if you take the infinite product okay, just expand it as a power series in X. You'll start off and you'll get some power series in X, and the nth coefficient Ramanujan denoted as tau m. Okay, and he made a bunch of conjectures. The first conjecture was that tau of n times tau of m is tau of n and m, whenever m and n are relatively prime. And the second conjecture was that tau of p to the a plus 1 was tau of p times tau of p to the a minus p to the 11 tau of p to the a minus 1 for every prime p. P is prime. A is bigger than or equal to. I guess it's a is bigger than or equal to 1. I think it should be okay. And 3 is that tau of p is always less than 2 times p to the 11 halves. So these were the conjectures that Ramanujan made in his 1916 paper. Okay? And these numbers, this function, you can calculate them. I mean, Ramanujan wrote down hundreds of them. And, before he made these conjectures, I guess he was looking at some numerical evidence in support of his conjecture. And they're very interesting numbers. They're natural numbers, of course, integers. They could be positive or negative. And shortly after he made his conjectures, these two conjectures were proved by Mordell. But Mordell, I suppose, didn't see that there was a general theory behind all this, and that was left to Erich Hecke to work out. And so Hecke so Mordell in 1917, and then Hecke in 1936, actually, 20 years after, worked out a general theory in which these two things were explained from a theoretical perspective, why they work. Why do you expect this multiplicative property all of a sudden just because of this stuff? Why should there be some sort of recursion relation like this? The third conjecture, of course, was the real doozy, and nobody really knew what this was all about. Until the 1950s, people started, people attempted in various ways of trying to prove the conjecture, but perhaps conceptual insight as to what the conjecture really means didn't open up until the late 1950s and early 60s, when a bunch of people, beginning with, I suppose, Eichler, Ihara, Igusa, a bunch of people, maybe I don't know the complete list of people here, started to realize that this was connected to the wave conjectures. That same wave conjectures that I talked about with the hyperkloosterman sums. So a link to the wave conjectures. See, again, you would never, never, never dream that this is the connected to these type of things. I mean, how mathematics is intertwined is really always kind of the beauty of mathematics. There are lots of surprises. So the wave conjectures all of a sudden appear, and the link was made in the 1960s. And when Deligne proved the wave conjectures, this came out as a consequence. And as far as I know, to this day, no one knows how to prove this except through this way of algebraic geometry and wave conjectures. Now, however, Langlands suggested a method of trying to understand the sequence. So this, as I said, if you're trying to understand numbers, a natural thing to do is to study these so-called moments. So it may be interesting to study what are called moments of the tau function. So Langlands. Well, suggested that we can kind of perhaps look at these objects. Because, as I said, the philosophy in analytic number theory is I give you a sequence of numbers, you try to understand them. One of the ways of trying to understand them is by studying these moments of these. Well, it turns out that when k equals 1, the study of this series really goes back to Hecke's work, the Hecke theory. For k equals 2, this was studied in the 1939, 1940 by Rankin and Selberg. And for k equals 3, 4, and 5, it is now known that this object has an analytic continuation in functional equation, just like the Riemann. It's starting to look like the Riemann zeta function. These things behave like the Riemann zeta function in certain aspects. They have Euler product, they have functional equation, they have analytic continuation, all sorts of interesting things. So for k equals 3, I'm not up to date on my record, but maybe up to something or other, up to certainly not more than 9, I think. We do know about these series, and they turn out to be interestingly fascinating, and they have analytic continuation functional equation. Now, because of the last conjecture, we could do the same Gauss sum kind of approach. So you could take your number tau of p, and you can now divide out by 2 times p to the 11/2, and that's a number between -1 and 1. And so you can write that as some cosine of some angle, right? And then the question is, as p varies, how do these angles distribute? Are they uniformly distributed? Are they equidistributed? Or are they not equidistributed? Okay, this is the question. So for a long time, people thought that in order to answer this question, you kind of had to go through this machine and get the whole mess. But it turns out that experimental evidence suggested that these things are not equidistributed, but they're equidistributed with respect to another measure. You have to put another measure on the something like 2 over pi, something like this, dx, instead of the Lebesgue measure. you should put this measure. And numerical evidence suggests that that's the measure that you should be using to study the distribution of these angles. These angles then become equidistributed with respect to that measure. Remember what equidistributed with respect to a measure means. You take a measurable function or a continuous function, you evaluate it on those angles, and then you take that sum and the limit, and it should go to the integral. Well, the integral was with respect to the Lebesgue measure, but now if you tack on this extra fudge factor, it turns out that that's probably the measure that it should work. And this was called the Sato-Tate conjecture. Because Sato and Tate made this conjecture independently, and they were led to it from various directions. And the miraculous event that took place a couple of years ago is that this is now a theorem. This is now a theorem due to Barnett-Lamb, Ghirotti, Harris, and Taylor. I hope I haven't left out anybody else. But bunch of people. It comes out, surprisingly, it's kind of like the post-Wiles developments. You see the opening of the door of modularity conjectures of Wiles and Fermat's last theorem. You have to push that even further and establish a few more modularity results. Once you do that, there's very nice analytic tricks. A good chunk of the final segment here is the Tauberian theorem. Non-vanishing of L functions finally gives you equidistribution. So this gives you some idea of how number theory has been evolving, especially analytic number theory in its relation to other parts of mathematics, especially to algebraic geometry, algebraic number theory, and representation theory. All of that stuff seems to be kind of, the grand synthesis is still in the offing, but clearly the whole field is sufficiently rich that there's a lot of work to be done, and perhaps some of you can contribute to that. Okay, so voila.